So today I'll be going through functional equations of around the IMO level, and so I'll be using some of my own notes and then going through some of the problems based on the solutions. So, well, this is my notes, and so I'll be going through this. So, functional equations, some of the basic techniques is first, of course, to substitute in the common values. And then so they can cancel out certain terms on both sides of the equations. And then it also helps to make, like, if you see some symmetry, you exploit like negative x to check whether the function is even or odd, or 1 over x when you see like, oh, the function looks like it can be cancelled out when you start in 1 over x. And so the next one is proving the injectivity and surjectivity. Injectivity is basically that, there's a one-to-one mapping that exists from the input to the output. Surjective says that, from the input, you can get to any single point in the output. Such a mapping exists. And if it's both injective and surjective, then the function is bijective. And it also is a very helpful property because you can then you have this one-on-one property, and so you're able to sub in different values to get this certain value that is like critical, or you know what it's equals to already. Okay, the other one is the Cauchy functional equation. Basically, when you have a function of this form, you know that the solution to this equation has to be of the form where it's like fx equals to kx, whereby k is a constant. And then it's very critical to remember to verify at the end of the question that every single one of your solution works. Otherwise, if you don't do it, then you might be deducted points for it. If multiple solutions exist, you have to be careful of the point-wise trap, because most functional equations require you to prove that different solutions cannot coexist. So if they do coexist, then you have to prove that it does not coexist by supposing that there exists like two different sets, whereby the first set is like for the first type of solution, the second set for a second type of solutions, and then when they coexist, you get something that's like an error, and it doesn't really work out. Okay, so the first problem is EGMO 2012. So looking at this immediately, usually at the start of the problem, I always like to say this. I think it's a good practice to have. Let P, A, B denote the assertion that something, something, something is true. Okay, so just like what I kind of said in the toolbox earlier, you substitute in values like 0, or you substitute values like 0 or minus x to see what goes on. So here I feel motivated to sub in 0, because if I sub in 0, then the y here entirely cancels out. Similarly for the y here. And so after I sub in 0, I realize that I get f(x) equals to 4x, which shows that the function is injective. I didn't really explain here, but I mean, usually for injective functions, you kind of suppose that if fa equals to fb, you want to show that a equals to b. So when fa equals to fb, ffa here obviously equals to ffb, which is equals to 4a, and this equals to 4b. And so this thing is injective. And hence, you basically use the function again, apply a function again, you get f(x) equals to f for x. And now, so now you feel motivated to sub in f0, because you realize that you can apply the property here. So you get like f3 times 0 equals to 4 f0 based on this function over here. And then it's also equals to f0 based on this function over here. And so f0 equals to 0. And once you get f is 0 equals to 0, now you try the other substitution, which is 0 and x. And so once you sub in f x equals to 0, you get f x, because here 0 is gone, here's x. And so this is equals to this. And now you want to sort of like make both sides like look similar, so you sub in x equals to 1, because like in this case, then you can remove this here, so you get f1 equals to 2f1, sub in 1 here, equals to f equals to 2f1 equals to 4, because here you get this is equals to 4x, so it's equals to 4 from here. Yeah, it gets a little bit messy, but then like all the statements from the previous parts do add up. So you get f1 equals to 2, and subsequently f2 equals to 4. Okay, so now you substitute in this, because you want to get rid of both sides, such that you get this equals to 4, because you know that it's injective. So because it's injective, you want to make this thing inside the bracket 2. And so after solving in, you realize that since this is equals to 4, you get this is equals to 2. And then after rearranging a little bit, you had fx equals to 2x. And then usually in this problem, you have to check your solution to see whether it works. But I didn't do it. But you have to remember to check. So check. And then, so you get like y 2x plus 2y plus 2x times 2 equals to 4x plus 4xy plus 4y squared, which does add up to the before. And so that's the first problem basically. So the first problem is a bit of injectivity and subbing. So you have to get familiar with this process. Okay, the second problem, Iran TST. So the second problem, I chose it because I think that it was a very nifty sort of substitution that instantly got a problem done. So again, same practice. You state the statement in front. And then you realize that once you sub in this, you get um you can cancel out you get to cancel out this and this side. So like what I said before, you have to learn the substitute so that you can cancel out the sides. And so you get this. And so instantly you get a solution already. You get either fx equals to 0 or fx equals to x squared. And so now we use this apply this method called the pointwise trap. So we have to let there exist a not equals to b, because if a equals to b, then it's kind of pointless, because the function cannot be equals to two different values. And AB not equals to 0, because when AB equals to 0, then they sort of like fulfill the same criteria for both. And so now you consider two different sets. So A belongs to the set A, where all the solutions correspond to 0, and B corresponds to B squared. So you substitute in, you get this. And so you see there is a function inside this. So either this equals to 0, but if this equals to 0, then B equals to 0, which fills. So the other case is that this gives you it's basically this squared. So then it gives you e squared equals to 2b. So since all the real numbers are either fall into a or fall into b, and if there are multiple values of b, then you can sort of imagine that this contradict the case whereby a squared equals to 2b, because if like say like if you have um like a equals to 4 and b equals to like 8. So A belongs to set A, B belongs to set B. But then if you have another value like say 1 instead of set B, it doesn't fulfill the condition that A squared equals to 2B. But so now you kind of force that OB can only be like one single, it can only be a cardinality of one set. But that cannot be true because you know that this function is also even. So since this function is even, then there has to be at least two inside of this set. If there is anything inside this set. So this contradicts everything. So hence the pointwise trap fails, and then you have px equals to 0 for all x, or px equals to x squared for all x. And then you have to check to see both solutions work. I simplify it to sort of reduce some time, but then you have to sort of like check to make sure that um your solutions do work, and then also check for the pointwise trap. So for this, um sub to cancel, and then second one is pointwise. Third is check. Yeah, these are like the learning points. Okay, for Q3 is a more interesting sort of problem. So Q3, essentially you have that all these functions are injective. So you would love to make like a right hand side a constant. So that once the right hand side is a constant, what is inside the bracket of the left hand side must also be a constant. So do the same, you sub in x and 0. Let's see what you get. And you're able to get like these three equations. And then you do some like switching around and stuff at the below part. Yeah, the below is like more tedious computations, but then you sort of realize that um you get this equation which is this is a constant and this is a constant. So once you sub this constant as a c, you're able to get f x plus c equals to f x plus c. And this is suspiciously linear, which it actually is. So and then you know this function inside of f(x) is a linear function. So since f(x) is a linear function, you can basically sub it equals to like x plus d, whereby d is an arbitrary constant. You sub it inside the equation, and then to try to get what's the value for g and h. So then you also get a g and h are also linear functions. Then eventually you obtain that like if G has a constant E, H has a constant F, you do some tedious whacking and you get D equals to E equals to F. And so the solution is, they are all linear functions with the same constant. And so you do some checking as well. Go back and do some checking. So, well, this is equals to Y plus D. This is equals to X plus D, Y plus D, this thing plus D. So it works. And D can be any sort of like arbitrary constant. And it's clearly injective because it's a linear function. Yep. Okay, so the learning points for this is sort of like injective and then like linear functions, I guess. Linear functions. Yeah. It's pretty straightforward once you get the right substitutions to connect all of these three equations together. Okay, moving on to question 4. Question 4 is SMO open 2014. So same thing, we let P(x,y) denote the assertion that is true. And then, well, we use the property that it's injective by comparing XA and XB. So we get A equals to B. And we also prove the surjectivity. Usually you have to go one step to prove the surjectivity. Otherwise you don't know whether it's bijective or not. But then in like the first question, you know that like it's like sort of like fxx equals to 4x, which clearly can reach any sort of real numbers. And so we improve the subjectivity because like since x can attain any real value, since x is any real value in the domain, So this function itself can also attain any real value. And we do some substitutions. We sub in x and 0. And then since like this is injective, so we get x f0 plus x equals to x. And so x f0 equals to 0, which gives you f0 equals to 0. And now you sort of want to like, oh, since I have f0 equals to 0, and this is like the only sort of known equation I have, so I want to make the right hand side equals to 0 so that I can get like what's inside the bracket of the left hand side equals to 0 as well. And so I do substitution of y equals to negative fx over x, and then I eventually get x, this thing equals to 0 by bijectivity. And so this thing is equals to negative 1. And hence, since this is also bijective, this is the constant. So negative fx equals over x equals to k, whereby k is like some arbitrary constant. And you sub it back to the functional equation, you get this. So you're able to get the two different values of k equals to plus minus 1. And again, you do have to check for pointwise trap. But then this one is like more simpler than question 2, because question 2 is mainly about proving the pointwise trap that makes the different question like more difficult. But this one, after you prove that it cannot give AB equals to, I mean it doesn't give AB equals to 0 for both, like both solutions cannot coexist simultaneously, then you're able to obtain that fx equals to x or equals to negative x for all values of x. And again, you check xy plus x equals to xy plus x, or xy minus x equals to xy minus x, which works. Yay. Okay. Now question 5 is it's a more number theory style question, you know, immediately when you see like prime numbers as one of its domains. So I think when you see this thing immediately, you always sort of think about like this AB equals to BA question, whereby the only integer solution gives you like AB equals to 1 1 and AB equals to 2 4, which is like somewhat, this idea is like somewhat related and provable by calculus. But then let's go about it the functional equation way. So again, similar thing. First prove the function is injective by supposing when FA equals to FB, such that supposing this is true. And so do you suppose this is true? You get like FA, FB plus AB, BA. Yeah, you're able to cancel out one side, and then you can get like AB, BA. AB equals to BA, which I again use the idea from above. You only have the solutions AB equals to 2 4. And well, how do you prove this thing? It's not really important, and if you really want to do it, you can just use calculus, honestly. Like, it doesn't hurt using calculus to do like math Olympiad problems, I personally think. So like you realize that once you sort of like differentiate this thing, the maximum point is equals to E and 1 over E. So E is like the maximum point. So like the graph itself, if I'm not wrong, will look something like this. So you want to find like what are two, like what's like the line that crosses like this graph at two different points, and what are the 2 points that it corresponds to. And so since this is like E and this line's like 1, because it crosses like the y-axis, something like 1. So you know it's between like 1 and E, and the only possible solution is like 1 or 2. But then you want it to be different, so the only solution is like 2 or 4, or 4 or 2. And so you get that it's injective. And now so you have like, so you want to work with like, oh, what happens if like it's uh an odd prime and an even prime? So you're able to get this equation here, and well, you rearrange a little bit, and you get this is like 1 mod 2. So you deduce that one of fx and f2 has to be an even number. And since it's injective, so you have f2 equals to 2 strictly, and you obtain this sort of equation over here. And again, you use calculus ideas, gx equals to 2. I know it's kind of poisonous to use calculus ideas, but once you look at this sort of like graph, it's also easier to use calculus ideas. And so you had gx equals to 2. Mm, equals to 2 to the power of x over x to the power of 2. And then you calculate its derivative, and you get it's strictly increasing. And so you realize that fx can only be equals to x, because otherwise, if fx is not equals to x, so you must get two different values. And hence, fx equals to x is the only possible solution to this question. And so what are the takeaway points? It's honestly, it's okay to use calculus. Yeah. Okay to use calculus, and then try from small cases. Small cases, like when you have primes, you go to the smallest possible, which is 2. Yeah, and then again, of course, check. But then once you apply in like fp equals to p, you substitute it into the equations, pretty straightforward looking. Okay, now the last one is an IMO problem, and of course it's tedious. I chose it because it's tedious. Well, it looks interesting because you have this condition a plus b plus c equals to 0. So you sort of like wonder, oh, what's the conditions must it fulfill? And the most immediate sort of like solution, I mean, sort of like substitution you can get is when you substitute everything equals to 0. And then you get like this thing. So you have s0 squared equals to 0. And then now you sort of want to like, oh, assume that c equals to 0. And then like you have one is like a and one is negative a. So hopefully you can get something out of it, like some even function thing. And it's like fa squared plus f negative a squared equals to 2fa f negative a. It's like, oh, this looks suspiciously like completing the square. And then, I mean, it's true. You complete the square, you get this is even. And then similarly, so you work with another substitution, which is like you assume that a equals to b, and then also c is equals to negative 2a. And you substitute in again, and then you lift out, you can cancel this out, and then you get this value. So the solutions are f2a equals to 0, or f2a equals to 4, f8. And then, oh, okay, so you have two solutions and you begin case whacking. So functional equations, you also need to case whack. So first you assume the formal, which is f2a equals to b. You suppose there exists some fb equals to 0. And then you substitute this b inside. So you get fa squared plus, oh yeah, you substitute in, and then you basically that this thing is equals to 0. And hence it's periodic with this being true. And well, so now you check for f1, because you know that when So when like you have like one -2 or something, you get like you substitute and you get like f2 and f2 minus 4 f1, something like that. And so when f1 is equals to 0, then fx equals to 0 with the interval 1. So basically it's a constant which fulfills the equation, so everything equals to 0. So well, first you assume that, oh, what if f1 is equals to 0? Okay, so when f1 is equals to 0, then based on this, then you get like fx equals to 0, so everything inside this thing is at 0. So basically fx is like a constant function. And then you check for f1 equals to k, whereby k is non-zero. So you substitute this in, and you get like 2, -1, -1, and then so f1 equals to k. So f2 squared equals minus 4k f2 equals to 0. So either f2 equals to 0 or f2 equals to 4k. But if f2 equals to 0, so it's like the interval is equals to 2. And so you do some checking, essentially like whacking or something. And then you get that this equation here is equals to like 0k, 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 blah, 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 blah. And that's when f2 is equals to 0. And when f2 is equals to 4k, which is the other case, you get like, you substitute this in again, 3, -2, -1, because it's like the most immediate substitution you can think of. And then you get two solutions again. Quite annoying. So first you assume this is true, and you realize that, oh, it repeats by interval. So you check again for the even intervals, and you realize that it does repeat by intervals. So it's like k 4k, k 4k, k 4k, and so on. And when f3 equals to 9k, you realize that it's like k 4k 9k. So it's like, oh, you have to prove that it's like k is x squared. And how do you prove that? You use strong induction. And once you get like, you start like n plus 1 and -n and -1, you realize that this thing is equals to 0. And then you're able to do another substitution again. Oh, sorry, I had to erase everything because I have to move on to the next page. You do another substitution on again, and you realize that fn plus 1 equals to kn plus 1, and then you prove the induction. So induction is true. So now you sort of like compile all these four solutions, which is fx equals to 0, f2n equals to 0, f2n plus 1 equals to k, and then f2n equals to 4k, and f2n plus 1 equals to 0, and then fx equals to kx squared. And then you realize that all of these solutions do not exist simultaneously, because k, which you assumed earlier, k now equals to 0. And you check for all of these cases to see where it works. Fx equals to 0 works. Kx squared works. And well, I'm sure if you stop in 2 and 3, it also works as well. And yeah, so that is basically IMO 2012, I think, the functional equation. And so the basic idea is case whack. And well, be careful, I guess. Be careful with the systematic listing. Okay, so I hope all of these problems have taught you something. And so this is like the question set I've prepared as well. And the first question, probably substitution. Second question, pretty sure you need some bonding ideas. You need some bonding ideas as well. And the question is pretty hard. Fourth question, also pretty hard. Also pretty hard. And fifth and fifth question a bit unique because it's a rational domain question to a rational range question. So certain ideas can be used because like usually when you think of rational, you think of Cauchy. So it might come in useful. And then this one also substitution. So yeah. basically this concludes like my functional equation sort of like lecture. And I hope like all the problem walkthroughs have given you all like a taste of what are each of the techniques that you need to solve these problems. Yeah, and that will be the end of the lesson. Bye bye.